In the previous video, we have seen the forward checking technique for filtering the all different constraints. Unfortunately, although it's very fast, it's not able to remove all the infeasible values, and it's not able to detect any unfeasible situations for the all different constraint. So now we will really design a global constraint for the all different constraint that is able to achieve domain consistency, so detect as soon as possible as there is an infeasibility for that constraint, and is able to remove all the additional infeasible values. Let's start with a small example that illustrates that the forward checking algorithm and also the binary decomposition might miss some possible filtering for the all different constraint. So I assume that you are very familiar and a good player of the Sudoku problem. So let's consider that this is one row of the Sudoku grid that you want to solve. Okay, and that's the current situation. So you know that you need to assign all the numbers from 1 to 9 in this row of the Sudoku. And that's the feasible values that are still available to you. Some of them are already fixed, okay? And so if you would play with a strategy that is exactly the same as the binary decomposition, so you can only consider 2 cells at a time to do your reasoning, then you will probably say, and you would be right, that you are not able to detect infeasibility in this row because everything looks good, right? If you take, for instance, x1 and x5, there is still a possible assignment that would make the two of them true, and that's the case for every pair of variables. If you consider the variables pairwise, you will always think that it's feasible for the not equal constraint. But if instead of considering it locally with binary constraints, if you consider it globally and you do a global reasoning, then you will probably detect something more there. For instance, what you see here is that the value 1, 2, 3, okay, clearly we know that they need to be removed because 1, 2, 3 has already been removed previously. This is why they are in red. But that's not the only thing that we can detect there, right? It's not the only thing because now what we have is that the value 4 and 5, okay? The value 4 and 5, you know that they will be taken by x1 and x3 together. You don't know if it will be 4, 5 or 5, 4, but you know that they will be taken by x1 and x3, right? Because anyway, you need to fix these values to one of the two variables. This is what the domain said there. So because of that, you know that 4 and 5 can also be removed from the domain of x5, because if I would assign a 4 to x5, I wouldn't be able to do it for x1 and x3, and that's mandatory because they only have these two possible values. Because of that, x5 now is fixed, and since x5 is fixed, I will be able to remove it from x6, there, x8 and x9. And now what we have there is that here, again, we see something that is interesting. 7 and 8 will be taken by x6 or x9. That's exactly the same, for the same reason as the one I already explained for x1 and x3. But we know that the 7 and the 8 will be taken by x6 and x9. And therefore, 7 and 8 should be removed from x8, and so this one becomes fixed to 9. Okay, you wouldn't be able to detect that with the forward checking algorithm without any search, right? Just at that level, you wouldn't be able to detect it. For the same reason, the forward checking algorithm is also not able to detect that there is an inconsistency in this situation. Okay, that's another situation. You have 3 variables. And the 3 variables can take the same 2 values. So you have only 2 values for 3 variables. Okay, so it's not possible to assign to the 3 of them a different value, and we should detect the inconsistency. But if you do the reasoning locally with binary variables, this one and these ones, then you wouldn't detect the inconsistency. So we need to have a stronger infeasibility detection for the all different constraints. And to detect this kind of inconsistency, we will first build a bipartite graph that we call the variable value graph. We put the variables on the left and we put the values of the union of all the domains on the right there. And we will add to this graph, to this set of nodes, we will add an edge between a variable and a value if this value belongs to the domain of the corresponding variable. So for instance here, you see that the 3 has an edge to x0 because 3 is a value that is inside the domain of x0. But there is no edge between 0 and 0 because 0 does not belong to the domain of x0. So that's the variable value graph. Okay, and to detect the inconsistency, we will implement a graph algorithm on top of this variable value graph. And the graph algorithm that we need is the one of the maximum matching. Okay, if we would be able to find a maximum matching in this graph, a matching of cardinality equal to the number of variables, then you know that the constraint is feasible, the AllDifferent constraint is feasible. What we mean by a matching is a set of edges in the graph so that no two node has an incidence degree of 2 in the set of edges that you have selected. And that's the case here. Okay, so the blue edges that I have selected there is a maximum matching. Okay, you see that there is no two node with two incident blue edges, right? Every node in this graph, in this solution, have a blue incidence of exactly 1. Okay, and so that's a maximum matching in the variable value graph. If the cardinality of this maximum matching is equal to n, the number of variables, then we know that there is a feasible solution to the AllDifferent constraint. So we shouldn't fail at least. Okay. I take this slide, I take the opportunity to define two additional notations there. I will say that this is a M3 vertex because it's not incident to a blue edge. Okay, that's a M3 vertex. That's a M3 vertex. These two ones there. Okay, and so the AllDifferent constraint is feasible if and only if there is a maximum matching of cardinality equal to the number of variables in the variable value graph. That's the feasibility check that we will use to detect an inconsistency in the AllDifferent constraint. And trying to find a maximum matching is not a very difficult problem in computer science. We can do that in polynomial time. Okay, so how do we find the maximum matching in a bipartite graph? Well, a first idea that you can imagine is we can use a greedy algorithm. So you will go consider all the variables from the top to the bottom. And every time you see that there is, it's not yet matched, you're trying to find a value, a node that is not yet incident to a blue edge. Okay, and this is what you will get. But with this greedy algorithm going from the top to the bottom, you might end up in a situation in which you will not be able to assign, for instance, the last variable, and still there exists a maximum matching of cardinality equal to the number of variables, although you wouldn't be able to detect it with this greedy strategy. And that's the situation that we have here. We see that 8 here, okay, we cannot assign it to this one because it's already matched. We cannot assign it to this one, and we cannot assign it to this one. But these three variable values were the only three possible values for the variable x8. And so you see that this variable is not very happy because it's not matched to any possible value. And still, there exists a maximum matching of cardinality n in this situation. So how can we find it? We need something a little bit more advanced, and that's the idea of augmenting the matching with an alternating path. The idea that we will now force an orientation of the edges. Every edge that are already in the matching, I will orient them from right to the left, and the edges that are not in the matching, I will orient them from the left to the right. So for instance, this one, you see that it's oriented in that direction. Then I will start here from an M3 node vertex, this one, for instance, and I will use a depth first search, okay? And by definition, by construction of the way I have oriented the edges, I know that the depth first search will only consider paths that are alternating between the blue edges and the black edges, okay? It's because the graph is bipartite and I have oriented the edges this way from left to right and from right to left, depending on their status in the maximum matching. Okay, so you try from there to detect, to find an alternating path. Okay, so you try to find an alternating path, and if you're able to find an alternating path that end up in one of these nodes, okay, so it means that the alternating path is with using an even number of edges. Okay, so in that case, once you have the alternating path, you just flip the status and the orientation of the edges, and you have increased, you have augmented the cardinality of the matching by 1. So let's see what it gives on this small example. For instance, this one, okay, it's an alternating path. Okay, you see that it's alternating between not in the matching, and then not in the matching, and it ends up in a node here that is also M3. You will flip the status along this alternating path, and so you will augment the maximum matching like this. Okay, so you flip the status. So by flipping the status, this is exactly what will happen. So this one will be now considering the matching, this one will not be in the matching anymore, and this one will be added in the matching. So instead of one edge that you have removed from the matching, you have added two different edges in the matching. So you did a +1 on the cardinality of the matching, and now every variable is matched, correctly matched. Okay, and so this is what you have there. And that's the idea of the augmenting path, and it's really an iterative procedure. You start with a matching, any matching, not necessarily maximum, and then you will iteratively augment the matching using the alternating path. So you start the depth first search from the M3 node, variable node, and if you are able to end up in a value node that is still M3, then you can flip the status of the edges, and you stop, you do that until you cannot find any feasible alternating path, and at the end you know that you have a maximum matching. If the maximum matching has a cardinality, a number of edges that is equal to the number of variables of the all different constraint, then you know that the problem is feasible. Okay, and that's really a nice algorithm that is polynomial, because it's polynomial time to find the maximum matching, but it doesn't tell you yet how to remove the edges that are infeasible, and that's the topic of the next video, and that's a little bit more advanced.